Today we're going to get more into modeling growth and decay, exponential variety. Okay, so a good warm-up type problem is, actually I should look and see what slides I'm supposed to be on. I don't even think I'm supposed to be on this slide. Nope, I'm supposed to start with that one. I knew I was supposed to start with a tractor problem. Okay, so
Your favorite.
Tractor problem. Okay, so Mr. Linsmeyer's accountant is figuring a depreciation rate of 5% per year on the farm tractor that tills the bean fields. If the tractor is worth $192,000 brand new, and that's actually quite a deal for that tractor right there. It's actually, that tractor that's pictured right there is probably about a $285,000 piece of machinery, at least. Okay. What is the value of that tractor after 14 years is my question. It's a great question. So let's go with that one. Okay. Depleting, depreciating. Depleting, depreciating. It's all the same. Okay, so talk to me about a formula here for, we'll call it T for tractor of, actually no, let's call it B. We'll call it beans. Beans of T. Okay, what's my formula? What's my equation? 192,000 times what? 0.95 to the 14th power. And what did we get when we get 192,000 times 0.95 to the 14th power? 0.60?
Yeah.
Okay, actually, yeah, okay, because it's 0.595.
Yeah.
Yep, okay. So then this tractor is going to be worth $93,633.60.
That's the same as equals 1 minus 0.05.
Yes. And then but that 1 minus 0.05 has to be in parentheses to the 14th power. You know what I mean? You can't just say this. It's got to be 192,000 times 1 minus 0.5 to the 14th power. Oops, 0.0. Guy can make one mistake. I mean, my God. Looking at a tractor. Yep. That's my jam. Okay? Yep. All right, logistical growth. Now, we've been talking about exponential growth, and exponential growth grows and grows and grows and grows and grows and grows, right? But like, let's talk yesterday, we had the population of San Jose or Columbus, right? Okay, and we were talking about the growth of that population. Now, if that population were to continue to grow and grow and grow and grow, would that be realistic? Why not? You can only fit so many people in a certain area, right? Okay? You can only, population growth, yes, it is exponential, okay? But we can only fit so many people on this planet. So it can't be unlimited growth. Okay? So what there is when exponential growth is unrestricted, okay? It continues to grow and grow, and it's not bounded above, okay? But many growth situations, there's a limit to growing, okay? There's only so many people that we can fit in this room, okay? We have limited space. So if we started pulling people in, we could show an exponential growth, because, you know, if we just start yanking people out of the hallways during passing time, we could show an exponential growth. But there's got to be a cap, because there's only a certain amount of people that will be able to fit in this room that we're in right now. Okay? So a plant or a tree. Okay? A plant grows, speaking as long as we're talking farming, my plant, the bean plants that we were referencing there, that's about a 2-month crop. Okay? Right? So you plant them, and then you pick them 2 months later. Well, they grow exponentially at the start because they get big fast. But then they don't continue to grow at that rate. Otherwise, I'd have, like, you know, trees in my field with beans on them, which I don't want that. Okay? Right? They can only grow so much. Population of a city won't grow exponentially forever. Sales of a new product. Well, once as soon, you know, like the new iPhone came out, and the sales for the new iPhone probably went off exponentially. But then that's going to slow down. Okay? Because the more people get it, the slower it'll go. In these situations, growth begins in an exponential manner, but eventually slows and levels off, and we call these logistic functions. So what a logistic function looks like is it starts out and it grows exponentially, but then it slows down and it caps itself off. An exponential function has a horizontal asymptote below it, right? A logistic function has a horizontal asymptote below it and above it. Okay? So it has a range of where the function is applicable, or where it can be. Okay? So we're going to dive now into logistic functions. Okay? So logistic growth functions can be labeled as either, I shouldn't say labeled, either one of those is a logistic growth function. Happens. Okay. So, for instance, let me put a for instance on here for you. Okay. So we use blue already. Let's use red. Okay. All right. So f of x equals 100 times 1 plus 4 times 2, oops, no, but it's got to be less than for it to grow. To the x power. So that would be an example of a logistic growth function. Over here, it would look like that. If we want a logistic decay function, then B on the left one here, this black 1/2 would have to be bigger than 1. Or this K value over here on the E would have to be positive. Okay? And then we've got a decay function. Now the cool thing is that I can tell what the lower bound is always going to be 0. Okay, so my lower horizontal asymptote is always going to be 0. Unless I have something out here after the function that would shift that horizontal asymptote. Okay? But for the basic one, that part right there, the horizontal asymptote is y equals 0. The upper asymptote is y equals c. Where do I get c from? The numerator on the fraction. Okay, so we get that. Okay, so then that tells you the range that it's going to be in. Okay? Whoops, hit the wrong one. There we go. So, example number 1. Find a logistic function with the following conditions. It has an initial value of 12. It has a limit to growth of 60. And the curve passes through the point 1, 24. Okay? So we're going to want one of the form f of x equals c over 1 plus a b to the x power. We'll do that one because we haven't really done finding k values yet with Do I know anything on there?
Yes.
What?
So C.
I know the limit of c, right? Okay. So 12, or what's c? 60 is c. Okay. So I know that. So I've used my limit to growth. What else can I use? Which one would be easiest to use next? The initial value, right? Okay. So the initial value says that it goes through the point 0, 12. Well, what's 12 and what's 0? What do you got? Okay, so what does that mean? Because yes, 12 is the y-intercept. Okay. Okay, so what would I do in my blue equation? A is 12. Do we agree that A is 12? I'm asking.
Exactly.
I'm asking. Do we agree
I'm
with
just
it?
gonna go with it. Yeah, I agree.
Yeah? I like that better. Okay? I'm going to plug in 12 here for f of x. And I'm going to plug in what? And 0 for x. B to the 0 power. 1 times A. A plus 1. 1 plus A, right? Okay, so that's just still 1 plus A. So this is 12 here equals 60 over 1 plus A. What?
Yeah, I was gonna multiply it. So
Multiply what?
do 1 plus A.
Multiply both sides by 1 plus A? Okay, because that'll get rid of the fraction. So we get 12 times 1 plus A equals 60. Ooh, even easier than that. No? Divide by 12. I divide both sides by 12. Yep. 1 plus A equals 5. A equals 4. Okay. So now, let me back up a little bit. See if I can get it all. Oh, look at that. I can get it all in there. Okay. So now we're at f of x equals 60 over 1 plus 4 b to the x power. Right? Because I found C and I found A. Now what? And do what? So what am I going to be?
Isn't it 60 over 1?
Oops, did I put 1? Okay, I can't, be.
Just make a 6 out of it.
How do you make a 6 out of the 1?
It's not that difficult, Joe.
Okay. B to the first.
B.
B. Okay. So that's just B. So how do I get rid of, or how do I solve that one for B? Multiply it by 1 plus 4b? Can't, because the 4's got the b attached to it. You ever seen that trick? Where you flip-flop those two? How is that legal? Well, let's look at.
Wait, let me figure it out.
Look over here, right? Right? Because so we flip-flop them, and so this would have become over here. Let me put it in red. So this would have been 1 plus A equals 60 over 12, right? If I flip-flop them, 60 over 12 is 5, so that puts me right down there. Okay. So what do we got? 5 over 2 here. 60 divided by 12 is 5. 24 divided by 12 is 2. Okay, so 5 halves there. So 1 plus 4b equals 5 halves. Subtracting 1. 3 over 2. Yep. So 4b equals 3 halves. Dividing by 4. 3 over 8. Let me fill in some. So we subtracted 1 here, which was really, we're subtracting 2 halves there. We divided by 4, which is really multiplying by 1/4 there, and we get 3/8. Love it.
So now we're done?
So now we're done, because now we've got our function. So our function is now f of x equals 60 over 1 plus 4 times the quantity 3/8 to the x power. Just so we see what that looks like, I'll quick graph that one here as soon as the old graph fires up.
I think it helps me focus sometimes.
So we've got a function here. Whoop, traffic breaks. We've got a function that is 60 over 1 plus 4 times 3 divided by 8 raised to the x power. Okay? So there that is. Hold on. Hey, focus back in. So I've got to change my window. Let's go out to 100. Okay. So there is my exponential growth. So it's showing my exponential growth. It goes through, if we found the 0 here, it would go through 0, 12, and it would go through 1, 24, exponentially growing, but then it slows and it flattens out. Yes, ma'am?
So the horizontal asymptote on top, do we find that, is it just 60?
60.
How do we know? Is it just always the top?
It's always the top number. Yep, it's the limit to growth.
Okay.
Yep. Okay. You now find me this one. All right, here we go. So I want f of x equals c divided by 1 plus ab to the x. I want that logistic. So my limit to growth is 30, so that makes this bc. Right there. Okay? So that tells me that I've got, if I want to use this one up here, my initial height, so that would be 5 equals 30 divided by 1 plus ab to the 0 power. So that we can actually see it. So we'll just do it this way. That works for me. Okay. B to the 0 power is 1 times a is 1. So that gets me 5 equals 30 over 1 plus a. Flippity floppity those two. Okay, so then this gets me 1 plus a equals 30 divided by 5. 30 divided by 5 is 6. So minus 1 is a equals 5 then. Agree? Okay. So now I'm sitting at f of x. So now I got to use my other point. So 15 here is going to equal 30 divided by 1 plus 5b cubed. One plus 5b cubed is going to equal 30 divided by 15. That's 2. So 1 plus 5b cubed is 2. 5b cubed is 1. b cubed is 1/5. So b is the third root of 1/5. Okay? Which, if that's what we're going to do it, if you want to be exact, boom, put it in. That would be what you put in your equation. So I would go here with my function as f of x equals 30 over 1 plus 5 times the third root of 1/5 to the x power. Okay? Or you could also go with, clear that out, the third root of 1/5 is f of x equals 30 over 1 plus 5 times 0.5848 to the x power. That's bad. I gotta hold on. I don't even like how any of that is written. I know, OCD, it's a real thing. Yes? Okay. Was that a good?
No.
Or was that a bad one?
No, I get this.
Oh, okay. Okay. Good?
I got lost.
Talk to me.
15.
The 15. You want me to do it a different way?
No, I just didn't. I did
Or you lost how you even got to that point?
I divided by 5. I didn't do that.
I don't know why you did that. Okay, because if I'm plugging in 15 there, right? So the other way of doing this here would have been, I'll go right down the middle. 15 times 1 plus 5b cubed equals 30.
I'm gonna plug it in 3.
Oh, that's why.
Okay.
Okay, and then divide by 15. And now I'm back to normal. Okay. Okay. Good ending spot, I believe, for today. So now you could start. Let me take a peek at homework packet here. You could now, for sure, interpret the meaning of the line intercept. You could do that. Yeah, you could do that. You could do numbers 6 and 7 now on homework